Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 12 today and looking at Section 12.2 on inverse functions. The objectives in this section are to determine whether a function is one-to-one, use the horizontal line test to determine whether a function is one-to-one, find the inverse of a function, find the equation of the inverse of a function, graph functions and their inverses, and determine whether two functions are inverses. And this is still SLOB, just like in the last section. And by the way, we're building up to the main topic of this chapter, which is exponential and logarithmic functions. As you will find out over the next couple of sections, exponential and logarithmic functions are inverses of each other. All right, so back to my favorite analogy, the same one that I used for the composition of functions. Let me show you how I do this with my airplane analogy. All right, so let's say one Christmas I get lucky and I get a direct flight from Sacramento to Philadelphia. Whoops. Takes a little practice drawing on top of a picture on this thing. All right, I get a direct flight from Sacramento to Philadelphia on flight F. And let's say that I get on at gate 7 in Sacramento and I get off at gate 18 in Philadelphia. So in the language of functions, that's saying that f of 7 is equal to 18. So when we talk about an inverse function, we're talking about a function that undoes what the original function does. So in this case, the inverse function would just be my flight home. All right. We call this function f inverse. This notation is kind of unfortunate because it looks like it says f to the power -1. That is not what it means. It just uses the same notation. We always read that as f inverse. So function f inverse would take me from 18 back to 7. And that's the idea. All right, so going back to the presentation. All right, now in order for this idea of an inverse function to make sense, the function has to be what's called one-to-one. So remember that in a regular function, with any function, no x value can correspond with one y value. Let me see if I can draw right on here for a second. Okay, so for example, it doesn't make sense for the x value 2 to go to both the y values, let's say 1 and 3. Okay. If you had a rule like that, it would not be a function. Okay. So, however, two x values are allowed to correspond with the same y value. So if you had x equals, let's say, 3 and 4, it would be perfectly okay in a function for both of those to go to the number 5. Okay. So you could have f of 3 equals 5, and you could have f of 4 equals 5. That is perfectly okay. However, if you wanted to make this function into an inverse function, then this type of thing would not be allowed, because what would happen? All right, remember that an inverse function is supposed to undo whatever the original function does. So in this case, with what I was just talking about here, the inverse function would be trying to send the number 5 back to the number 3 and also to the number 4. So then it would not be considered a function. All right, so in order for a function to be one-to-one, we don't allow that. In a one-to-one function, each y value may only correspond with one x value. All right, so for example, here are a couple of functions written in ordered pair notation, and we want to determine whether each of these is one-to-one. And then let me show you what the next question is going to be after that, so I don't have to make so many trips back and forth between here and the tablet. After we determine whether each of these functions is one-to-one, we're going to plot those points on a graph and see if we can come up with any kind of relationship between the idea of a function being one-to-one and its graph. All right, here we go. So the first question is, are these functions one-to-one? All right, well, when I look at the first function, I see 1, 2, 3, 4, 5 different y values, okay? So it is not possible for one y value to be associated with two different x values because all the y values are different. So this first function is one-to-one. However, the second function, which you may recognize as y equals x squared, right? That's the relationship between x and y in each of those points. Here is one ordered pair with a y value of 4, and here's another one, and that y equals 4 goes with two different x values. This one is not one-to-one. Okay, so now let me try something here. All right, so when I go to plot these points, starting with letter A, I have -2, 6, right about there, -1, 1, 0, oh no, I messed that up. Let's start over. All right, -2, -6. There we go. -1, 1, 0, 2, 1, 3, 2, 10. All right, so we have 5 different y values, which means if I were to draw a horizontal line through any part of this graph, it is never going to hit more than one point, okay? On the other hand, letter B, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. I can draw a vertical line, for example, a horizontal line, sorry. For example, there, and it hits more than one point. So that's what's called the horizontal line test. Remember, we used a vertical line test to determine whether a graph represented a function. So now we have a horizontal line test to determine whether it's a one-to-one function. All right, so the horizontal line test says if every horizontal line intersects the graph of the function at most once, then the function is a one-to-one function. So we can look at some easy examples here. By the way, this first one is an example of what's called an exponential function. We're going to be looking at those in the next section. All right, so if I start drawing some horizontal lines over this thing, I think you will agree that none of these horizontal lines hits more than once. You might start to question that when you get towards the bottom because the graph gets very flat. Okay, but it never gets perfectly flat. So for that reason, this function is one-to-one, this exponential function. However, the second one is not a one-to-one function. It is a function. It passes the vertical line test, but I could draw a horizontal line, for example, right here, and it hits 3 points. As long as it hits more than 1 point, it is not a one-to-one function. And then finally over here, this is the graph of the square root function. And no matter where I draw a horizontal line, it never intersects more than once. So this function is also one-to-one. All right, so this one is, whoops, let me try that again. Okay, so this one is one-to-one. This one is one-to-one. This one is not one-to-one. All right, let's see what's next. Nope. Okay, so the inverse of a one-to-one function f is the one-to-one function called f inverse, consisting of ordered pairs y comma x, where x comma y belongs to f. So remember what I said right at the beginning, this function f inverse is supposed to undo whatever the original function does. So in my airplane example, I went from gate 7 to gate 18. So f of 7 equals 18. That means the ordered pair 7 comma 18 belongs to function f. And if function f is going, f inverse is going to undo that, then the ordered pair 18 comma 7 would belong to f inverse. All right. Here's another example. This is the function we were looking at earlier. We said this one was one-to-one. So if function f consists of these 5 ordered pairs, then f inverse would consist of these 5 ordered pairs. So notice that the x and the y has just been switched within each ordered pair. All right, so now we get to the point of how do you find the inverse of a function? If the function is defined by ordered pairs, it's really easy. But what if it's defined by an equation, which is usually how our functions are defined? Well, there's 4 steps. 3 of them are always very easy. The other one is sometimes easy, sometimes not so easy. So first we replace f of x with y. Remember, f of x and y usually mean the same thing. Then we interchange x and y. So this is really where we change f into f inverse by switching the x and the y. All right, now this is the step that sometimes takes a little bit of effort. Solve that equation for y. Sometimes this is easy, sometimes it's a little harder. And I've got 3 examples for you. And then at the end, you're just going to replace y with the notation f inverse of x. All right, so here are the 3 examples we're going to look at. Let's switch back to the tablet. There we go. Okay, so first example, f of x equals 4x plus 9. Step 1, replace f of x with y. Y equals 4x plus 9. Step 2, interchange x and y. X equals 4y plus 9. Okay, step 1, step 2. Step 3 is to solve this equation for y. So the first step is going to be to subtract 9 from both sides. That gives me x minus 9 equals 4y. The second step is to divide both sides by 4. And that gives me y equals x minus 9 over 4. That equation is now solved for y. I'm ready to write the equation of the inverse function, which is step 4. That equation is f inverse of x equals x minus 9 over 4. Pretty easy, right? I'd say on a scale from 1 to 10 for this type of problem, this one's about a 2, right? So this is about as easy as they get. All right, this one's probably about a 4 or a 5. Still not that hard. Step 1, replace f of x with y. Step 2, interchange x and y. Step 3, solve for y. All right, so how are we going to solve this thing for y? Well, I guess we should start by adding 1 to both sides, which gives me x plus 1 equals y cubed. All right, so how do I make a y cubed into a y? Well, we can just take the cube root of both sides, right? All right, so why don't we switch to a different color here? We're taking the cube root of both sides. Remember, the cube root of y cubed is just y. So that gives me y equals the cube root of x plus 1. So the equation of this inverse function is f inverse of x equals the cube root of x plus 1. All right, last but not least, I'd say on a scale from 1 to 10, this one's maybe about a 7 or an 8. So they probably won't get much harder than this. All right, I'm going to try to write a little bit smaller because I have a feeling I'm going to need more room. So let's go over here. Step 1, replace f of x with y. Step 2, interchange x and y. Okay, now it gets fun. Step 3, solve that equation for y. Well, this is a good chapter 7 problem, actually. This is a rational equation in y. We have y in the denominator. So the first thing I'm going to do to get y out of that denominator is I'm going to multiply both sides by 2y plus 4. So that's going to give me x times 2y plus 4 equals, those are going to cancel and leave me 7. All right, now there are a couple different ways you could go from here. I think what I'll do is divide both sides by x. Remember, I'm trying to solve for y. So that is going to give me 2y plus 4 equals 7 over x. All right, now I'll subtract 4 from both sides. That's going to give me 2y equals 7 over x minus 4. And now if you want to think divide both sides by 2, that's perfectly okay. I'm going to do it a little differently because I don't want to end up with a complex fraction. But what I'm going to do is the exact same thing. Instead of dividing both sides by 2, I'm going to think of it as multiplying both sides by 1/2. It's just a little shortcut. Again, helps you avoid a complex fraction. All right, so that is going to give me y equals. Now you could leave that right-hand side just the way it is, or you could distribute the 1/2. I'll distribute the 1/2 and then we don't have to use parentheses to write the answer. That would give me 7 over 2x minus 1/2 times 4, which is 2. See what I did there? And we're done. That equation is solved for y. So the equation of the inverse function is f inverse of x equals 7 over 2x minus 2.